Welcome to Ask and Learn.
We want to sketch the graph of y is equal to x squared plus 5x divided by 25 minus x squared. Now, in this chapter, they give us a laundry list of steps that we can follow to actually graph this. So let's go ahead and just follow those. But before we do that, anytime you have a rational function, it's always a good idea to factor the numerator and denominator to see if we can get anything to cancel out so we can know where we have possible holes at. And we'll also need to factor the top and bottom to find our vertical asymptotes as well as our zeros of the function. So let's go ahead and do that. So the numerator we can factor out an x. We'd have x plus 5. And in our denominator, that is the difference of squares, so it would be x plus 5 and 5 minus x. So notice these x plus 5s are factors, so they can cancel out. And we'd be left with x over 5 minus x. And we should say that x cannot equal to 5, or negative 5. All right. Now, working with x over 5 minus x, as long as x is not equal to negative 5, is a much easier function to work with than what we had. All right, so now the first thing they tell us is to determine our domain. So in rational functions, that's where the denominator is not equal to 0. So we already found one of them being negative 5, and our other value would be where 5 minus x is equal to 0, or just 5. So our domain in this case is going to be negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. The next thing they tell us to find is our intercepts. So let's go ahead and find our y-intercept first. So y-intercept, this is when x is equal to 0. So we're going to have y is equal to 0 over 5 minus 0, which would be 0 over 5, which is just 0. Now to find our x-intercept, we're going to go ahead and set y equal to 0. So we'll have 0 is equal to x over 5 minus x. And now, no matter what we plug into the denominator, we can never make this function equal to 0. So we would just set it equal to the numerator, and that would imply that x is equal to 0. So our only intercept in this case is going to be 0, 0. Right. Next, they want us to determine if there's any symmetry in the problem. So we know rational functions won't really be periodic, but we can at least check to see if it is even or odd. So we want to look at f of negative x. And doing that, we would get negative x over 5 minus negative x, which is going to be negative x over 5 plus x. And you might notice that this here does not equal to f of x, nor negative f of x. So that tells us we are not symmetric about the y-axis or the origin. Now, the next thing they want us to find is where our asymptotes are. So asymptotes. So we can look at first our end behavior, so the limit as x approaches infinity of f of x, and I'm just going to call f of x our function y. So since this is a rational function, we know that since they have the same degree in the top and bottom, we would just divide the coefficients. So it's going to be 1 over negative 1, or negative 1 as x goes to infinity, and we get the same thing for going to negative infinity as well. So what I'm going to do is, let me go ahead and move infinity over, and I'm just going to put a plus or minus. So going to plus infinity or minus infinity will give us a horizontal asymptote at negative 1. Now, we can go ahead and check for our vertical asymptotes. So we know we're going to have a vertical asymptote where once we factor and simplify, this function here, the denominator is equal to 0, so where x is equal to 5. So we need to look at what happens as we approach this function from the right and the left of 5. So f of x. So this is going to be 5 from the right over 5 minus 5 from the right. And 5 from the right will be a positive number, so I'm just going to put a little positive sign right here. And then subtracting 5 minus something to the right of 5 will be negative. So this here we know will go to negative infinity. And looking at the other side, so the limit as 5 approaches, or as we approach 5 from the left of f of x, well, this is going to be 5 from the left, and then 5 minus 5 from the left. So, once again, 5 from the left is still going to be a positive value. But now when I do 5 minus 5 from the left, well, if we take a number slightly smaller than 5 and subtract it from 5, well, that's going to be positive. So this here is going to go to positive infinity. All right, so we have our asymptotes. We know our horizontal, and we know how our vertical asymptote is going to behave. The next thing we want to find, so this was steps 5 and 6, where the function is increasing and decreasing, and local max/mins. So to do this, we are going to want to find y prime. So let's just go ahead and do this on another page. So we have y is equal to x over 5 minus x. So if I want to take the derivative of this, I'm going to have to use quotient rule. So the way I remember is low d high minus high d low all over the square of what's below, where the d is just supposed to be derivative. So 5 minus x times the derivative of x minus, then them switch, so x d by dx of 5 minus x all over the square of what is below. Right. Now we know the derivative of x is just going to be 1. The derivative of 5 will be 0 since it's a constant. The derivative of negative x will be negative 1. So this here is negative 1. Now we'd be left with 5 minus x plus x over 5 minus x squared. Now these negatives cancel out here, and we're going to be left with 5 over 5 minus x squared. And we should keep in mind that this here, x cannot equal to negative 5. And that's just because y here is not defined at negative 5 either. All right, so something we need to do is look for critical values. And we can't set this function equal to 0 since we have nothing in the numerator that will make it 0, but we can possibly check what makes the denominator equal to 0. So 0 is equal to 5 minus x, which would tell us x is equal to 5. So this is a possible critical point. But we know that our original function, y, is not defined at x is equal to 5. So in this case, we actually have no critical points. Right, so now let's go ahead and put this over here. So we end up with 5 over x minus 5 squared. And doing this, we want to find first. So let's look for interval of increasing. Well, this is where y prime is going to be strictly larger than 0. Well, x minus 5 squared will always be positive or equal to 0, and 5 will always be positive. So this function here is actually always going to be strictly greater than 0, since the denominator can never make this 0. So this will be negative infinity to negative 5 union negative 5 to 5 union 5 to infinity. And remember, we don't include negative 5 and 5 since they are not in our domain. And so this tells us for where this function is decreasing, there are no interval of decrease. All right. And so then also because of that, we can go ahead and say no local max / mins. All right. Now the last thing they say we should do is look for concavity, as well as our inflection points. So that means we want to look at what y double prime is equal to. So let's go back over to that page and try to take the derivative of the first derivative. Now, first, I'm going to go ahead and factor that 5 out front. d by dx of, and remember we can rewrite 1 over 5 minus x squared as 1 over x minus, or x, yeah, so first x minus 5, since we can switch the 5 minus x since it's being squared, and put that to the negative second power, like that. And to take the derivative of that, we can go ahead and use power and chain rule. So we will end up with 5 times d, so the power I'd multiply out front will be negative 2. And then x minus 5 now to the negative third power. And then we need to take the derivative of what we have on the inside, which is x minus 5. Now the derivative of x minus 5 is going to be 1, since derivative of x is 1, derivative of 5 is 0. And now we can go ahead and combine these to get negative 10 over x minus 5 cubed. All right, so let's go ahead and write this on the other page. So we get negative 10 over y minus 5, or x minus 5 cubed. So for concave up, we want y double prime to be strictly greater than 0. So I went ahead and just solved this already. And that would give us the interval. So in other words, we want the denominator to be negative, and that would be when x is less than 5. So this is going to be negative 5 to negative 5 union negative 5 to 5. And remember, we don't include negative 5 due to us canceling out an x plus 5 term. All right. Then, to find concave down, it's going to be where y double prime is strictly less than 0, which would just be when x is greater than 5. 5 to infinity. All right. So this was the last thing they told us we should do before we actually start graphing. So now let's go ahead and begin graphing this function. All right, so let's go ahead and plot our asymptotes first. So we know at x is equal to 5, we should have a vertical asymptote. And we know at, actually let me go ahead and write that, x is equal to 5. And at y is equal to negative 1, so y is equal to negative 1, we're going to have a horizontal asymptote. Now let's plot our intercept, which is going to be 0, 0. So we know we have no symmetry about this function. We know we have no local min or maxes, and we also know we're going to have no points of inflection. So we already have everything plotted that we need to know, and we can go ahead and actually start applying stuff. All right, so for our asymptote, we know to the right of 5, we're going to be coming from negative infinity. So we're going to come from negative infinity like this, and then we need to approach our horizontal asymptote since there's no points of interest to the right of 5. Then on the other side of x is equal to 5, we should be coming from positive infinity, and then our point of interest is going to be the origin, since that is the intercept, and then we're going to approach our horizontal asymptote. So you could go ahead and maybe plot a couple of actual points on this, but since we're just trying to get a sketch of this graph, I don't think we need to be too accurate and just kind of talk about the important points like this here.